Hello everyone, Namaste. I am Ramnath who would like to share with you some information on the VLSI design topic, probability density and its impact on design yield. This is part 2. Part 1 is already available. Please feel free to provide your comments or any suggestions. Thank you. Variation is part of Mother Nature. No two are alike and everything is different. This poses an opportunity for some, and for some it is definitely a problem. To exemplify this variation, here the lobsters are shown. All these lobsters are in true colors and they are collected by David. Okay. How much ever they want to make each die to be same in the wafer, there will definitely be some minute difference between die to die, and thus variation will be part of the semiconductor wafer and the die. So as we know, there are different phases in the implementation of the design. In the digital especially, the STA removal and STA static timing analysis hold are different phases, like that physical design antenna which is damaged due to the charge buildup, and physical design DRC, clock domain crossing, electrostatic discharge, or and several other phases of the design implementation are part of the design where defects can come into play. So these defects are part of design implementation. Aside to these defects, there can be defects due to manufacturing. That means, like, during manufacturing of this die, there can be defects, and there can be defects even in the materials which are supplied to the manufacturing. So any of these defects can also impact the overall yield. So Six Sigma tools and methodologies help the business processes in reducing the defects, and thus they improve quality and efficiency. So if you see the defects in materials, the DPPM, say assume the number is say A designated. So DPPM stands for defects in parts per million. Similarly, there can be defects in manufacturing. Assume it is represented by B, and in implementation by C. Then you will observe that the total yield or rolled through yield will be YA star YB star YC. YA is related to DPPMA, YB this YC. So this is the total yield, because all these processes are in series. Hence, the multiplication is applicable. In the coming slides, we will discuss how yield and DPPM are related, and how the resulting sigma is also related, we can figure out. And in the coming slides, we will figure out how one of the stages of design implementation, which is STA hold, we will discuss further. And in the STA hold, how its probability is distributed and how it affects the yield, overall yield, we will know further. So as we know, STA hold between a register to register timing path, there can be so many gates here. Okay, so it depends upon the temperature at which this whole thing is operating, at what voltage it is operating, it depends, and the slew. It doesn't mean that the slew or the capture flop only affects. It also depends upon the slew at these instances. There can be instances here. At these instances also slew, the overall hold of this timing path will be affected. Okay, so coming to the high level goal to reach a low DPPM for this system. So we need to understand that the one of the stages in the entire system is STA hold. There are other related systems or the stages such as power consumption phase, DFT phase, or physical design phase. There can be other phases also. So they are all interrelated. That means like the process, temperature, voltage, slew, all these things can affect power consumption. It can affect the DFT or the physical design. So, and the power consumption stage will affect the STA hold, because if there is too much of power consumption, the voltage drop will be high, and sometimes the temperature rise in the chip also will be high. So these two will later affect the hold. So we need to ensure that power consumption should be reasonable enough so that it will be in the tolerable limits of increase in voltage and temperature, so that STA hold considerations will be still valid. In the same way, physical design also should be in such a manner that the power consumption, what is the power grid used, all those things should not overburden the physical design. So these phases are interrelated. So we need to know that their yield due to one phase will affect the overall yield of the system. So this is the interdependent system. That means like the effect of one will impact the other parts of the system. So if you want to get higher yield for the system by tuning one stage to a very low DPPM, then what will happen is like you will be increasing the design area and power to meet that. Definitely you will be able to achieve low DPPM and hence high yield. So but what happens is like the second stage, say for example physical design or DFT or power consumption, these things will be the bottlenecks. Then overall yield depends upon the next phase. So that means like if power consumption or DFT, based on that the overall yield depends. So we need to understand that all these stages yield should be overall same, or slight, one can be slightly better or not to be completely variously variedly different. As observed in the earlier slide, we know that different stages in the chip design will affect the yield, because there can be many defects in the different stages of the design and implementation. Before we go further, defect refers to a flaw or discrepancy in the phase of the chip. So more than one defect can be found in a chip. So a defect can exist in a DRC, defect can exist in an antenna or a CDC or in a hold or something. And defective means it refers to a decision made that a chip is unacceptable, typically based on accumulation of multiple defects. There can be more than one defect in a chip. So based on these defects and the severity, the chip is considered defective. So going further, so uh, the process baseline sigma will determine what is the yield it will give. why we bother about the process baseline sigma means we will know a little bit more in the coming slides. Like there are so many stages in the chip design, and all these processes, if they will have a variation. Variation is normal. So how those are contributing defects. So that is how the yield will be determined. So we need to figure out the defects per million opportunities. Thus, we can figure out what is the resulting sigma of that process. So based on that, we can predict the yield. And this will also help us if the sigma is low, it will help us in tuning the process. So based on the number of units the process produces, and based on the number of defect opportunities per unit, and based on the total number of defects, the DPO is calculated, and hence the DPMO is calculated based on the million opportunities. So we will take one example and connect these dots. Before we go further, I just wanted to mention that assuming this is a normal distribution of a DRC phase, so for example, so you will know that the distribution is in this way, and there are some parts which fall within -1 sigma to 1 sigma. Here this is the mean, and there are some parts which fall between -2 sigma to +2 sigma. Like that, different parts can fall between these sigmas. So based on these, where the sigma ranges, you can have pass percentage. So for simplicity, we will take one item. So here between +1 to -1 sigma, that means like between -1 sigma to +1 sigma, all these parts what fall belong to 68.27%. Hence, if you take 100 minus 68.27, you will figure out that 31.73% still fall outside +1 sigma, outside of -1 sigma. So those many parts, so 31.27 exists in 100. So in a million, these many parts exist. That means like these are defects. Okay, but if you go to -2 sigma to +2 sigma, then within this -2 sigma to +2 sigma, then it covers close to 95.45%. So the number of defects parts per million will be very less now compared to this one. So again, going to -3 sigma to +3 sigma, the pass situations are 99.73%. So you have only 0.27% are defects. Because of that, the total number of defects per parts per million are 2700 for 100.273, then for million. So in that way, we can figure out that for sigma 6 sigma to -6 sigma, the number of defects parts per million are 0.002. That means like 2 parts per billion. Okay, so this is how the different parameters DPMO, yield, and sigma are related. Sample size impact on DPMO. Many a times we have seen the election predictions, and they were not up to the mark in the sense of the amount of predictions they made, and they are not coming same as what is actually witnessed. The reason being, the election predictions are done with a small sample, and the election happened with a large population. So we need to know that how the samples have been considered does matter. So we need to ensure that when you are considering the samples, the places where there are swing votes or swing situations, those things need to be considered as part of the sample preparation, as part of the defect estimation. So we will consider further now how all these things will play a role. So DPMO depends upon total number of defects found on a sample by total number of defect opportunities in the sample into 1 million. So this is the total number of defects found in a sample. That means like if you have sampled some 40 wafers or something, then you have figured out that some number of samples have been defective in the, so those many dies in different wafers, from those different wafers they were defective. And however, you need to know that the total number of defect opportunities in the sample are so many only, because it depends upon the sample size. You are not polling the entire population of the wafers and dies which the product is shipped. Okay, so you should know the difference between a sample and population, hence how close it is. That means like we don't need to ensure that sample size should be equal to population size. It should be a correct representative. So DPMO can also be written as total number of defects found in the sample by sample size into number of defect opportunities per unit in the sample. So for example, if you take there are 26 defects in a specific scenario. Assume there are 26 defects found in a sample analysis, and the sample size is only 10. However, the number of defect opportunities per unit, that means like one sample, how many defects opportunities can be possible is 15. So we have to consider 26 divided by 10 into 15 into 1 million. So these many defects per million opportunities exist. So that is how DPMO is calculated for a situation. However, in the case of IC design, the DPMO is calculated, should be calculated in a different way. Assume that we are considering the same hold timing path. Each hold timing path scenario is different, because each hold timing path analysis is individualistic. It is not like if there are 100,000 timing paths exist in the design, that means like you have 100,000 defect opportunities exist. Okay, if you process all these things in the same way, that means like if you have same 100,000 timing paths replicated in different scenario, then it is same. But in a usual design, these 100,000 timing paths are unique. That means like what signals flow it receives, what is the composition of the cell instances, all these things are unique. So we should not be considering that these are all same. Here are some references that I have gone through, and it have really helped me in understanding some of the key concepts. Feel free to go through a few of them at your convenience, and don't hesitate to ask me if you have any questions. I will be sending the other parts in the coming days. Thank you.